All right, I'm very pleased to welcome Andy Chou, who is the co-founder and chief technology officer of Coverity, which is a leading provider of software quality and security testing solutions.
Sorry, Michael. It's actually Andy Chou.
Oh, thank you. Let's start over again.
Just want to make sure the name doesn't get to 15,000 people. Not quite right. So.
Yeah, absolutely. Thanks. Okay. So I'm very pleased to welcome Andy Chou, the co-founder and chief technology officer of Coverity, a leading provider of software quality and security testing solutions. We're going to talk to him today about a bunch of the stuff that Coverity does to make software better by using tools like static analysis. So Andy, welcome.
Thanks for inviting me, Michael.
Thanks so much for taking the time to speak with us today. I'm sure that all of our viewers are going to really benefit from your feedback. So prior to co-founding Coverity, Andy was instrumental in developing the core intellectual property behind the Coverity platform while he earned his PhD in computer science from Stanford University. And since then, he's developed many key innovations in Coverity's products. And prior to earning his PhD, Andy earned a bachelor's in electrical engineering and computer science from Berkeley. So Andy, in my software security course, we're looking at common security problems in software like buffer overflows and SQL injections and format string attacks. And we've also started to talk about tools and methods that developers can use to write software that avoids these problems. So hopefully makes it more secure overall. Among these methods is static code analysis, and Coverity, the code advisor tool, is an industry leader in static analysis. So I'm wondering if you can briefly explain to us what static analysis is and how it features in Code Advisor to identify security issues.
Well, static analysis is really just a broad name for a suite of different technologies that analyzes programs without executing them. And that can encompass many different kinds of things, including things that your compiler typically would do if you're using a statically typed language to check the types that are used properly. But it can also include very advanced techniques such as data flow analysis, control flow analysis, that go beyond what a compiler would typically do to find defects. And so it's a very broad rubric, and underneath it you can take a look at many different specific technologies all around essentially helping find more bugs of many, many different kinds. Inside Code Advisor, we use data flow analysis to find how data flows through the application and potentially find tainted data flows, for example, where potentially untrusted data is used in an unsafe fashion. We also use other forms of analysis to detect control flows where operations are used incorrectly. So, for example, you might have memory leaks in a program which allow the program to essentially lose track of memory that's been allocated, and many other kinds of defect types as well. So there's essentially many different kinds of analyzers that fall under the rubric of static analysis.
Okay, great. So you gave us some nice examples of what Code Advisor looks for. Tainted data flows is something that we talk about in the course a lot. That is that many security issues arise because data that should not be trusted, that comes, say, from the user over the internet, is trusted to conform to a certain format and then is used to overrun a buffer or used as a format string or something like that. So I can imagine that static analysis in identifying so-called tainted or untrusted data flows would be really useful. And that leads me to wondering how general is the technology that the tools that you develop use? In other words, is there sort of a core technology that many different security issues take advantage of, or are each of the analyzers you spoke of really sort of independent?
I would say that there's a handful of core engines, right, in our static analysis product in particular. One of them is a global interprocedural data flow analysis engine, right, that can track data across procedure calls and through the heap and things like that to some extent. And that's very useful for problems like SQL injection, cross-site scripting, these typical tainted data flow problems. There's also a separate analyzer that essentially analyzes the program bottom-up by summarizing function behaviors and then using those summaries when analyzing callers of those functions. And that's also interprocedural, but it's not producing a global data flow graph. And that's very useful for detecting control flow type problems. And usually we consider certain kinds of issues, such as certain kinds of buffer overflows, fall under that category. So there's a few core engines that are very commonly used across all of our different checks. And then there's some oddballs, like things like dead code, for example, use a somewhat different analyzer engine because we found that detecting dead code is a little different from the other properties we're looking for. Another exception is copy and paste that uses a different detector than our others, because copy and paste errors work differently than typical flow errors.
In the dead code elimination one, or dead code detection, is that something that you might run before running the other analyses, so they end up looking at less code?
Right. That is the question. Sometimes we get asked if that helps make the analysis more efficient. But we found that it's not really useful for that purpose, because it's very hard to tell what code is not going to get executed from our perspective. From a purely static point of view, any function that is potentially exported is potentially called, because this might be a library that we're analyzing. So it's very difficult to tell if it's something we can truly just skip. So we don't really skip anything when running our other analyzers.
Got it. What do you think? I can imagine that static analysis would be useful because it's analyzing the code before it runs. How does it fit into the pantheon of things that you might do to assert that to give yourself satisfaction that your program is secure, compared to things like manual code reviews or penetration tests? How does static analysis fit in? How does it compare to those things?
Yeah, I mean, there is no panacea for security, right? There's no single technique or approach that will solve all your security problems, and that is also true of static analysis. I would characterize it as sort of part of a complete breakfast, if you will, right? So you have many different techniques. Yes, manual review is definitely a technique that should and does get used in practice. But the problem with manual review is that it's very inefficient, right? It's very costly to review every single line of code with an expert who actually understands all the different potential security vulnerabilities. Really, there's very few people in the world that know about any particular type of vulnerability in depth. So it's very hard to get the level of review and the coverage that you need through manual analysis. Dynamic analysis is another approach that is very commonly used, and this can mean different things. One of the most common meanings of it today is for web applications to have a sort of scanner that will probe an application by crawling through the different pages your application has and essentially trying to attack it with malicious inputs to see how the application responds. When it works, that's fantastic, because then you get an actual example of an attack, and as a developer you have verifiable proof that you have a vulnerability, right? And that's nice, but that's the plus side. The downside of it is you don't get very good coverage of your application typically. So it's hard for dynamic analysis to reach all the nooks and crannies of the behaviors of your application. Static analysis, the strengths are that it covers all of the application, right? It can analyze every piece of code, every potential corner case. The downside, if you will, is that because it's trying to analyze the program in abstract, it can have what's known as false positives, right? These are reports that it thinks are real defects or vulnerabilities, but aren't really a problem in practice. And it's up to the developer to determine if they're real. And depending on the analyzer you use, it can take time and memory to analyze a large program. And so scalability for very large programs can be a concern as well. So
I imagine that scalability also trades off, and maybe the false positives issue as well, with the precision of the analysis. That is to say, sort of the how fine-grained the properties are that it tries to figure out.
Absolutely. I think that's one of the central challenges of building static analysis, is how to make it scale up to realistically large programs, at the same time having a reasonable false positive rate so developers don't lose interest. And also, not missing things, right? There's false negatives as well. You might miss defects, and in real life, static analyzers don't find everything in practice, and that's a deliberate trade-off in order to be able to have these other properties that we also find desirable. So it's a balancing game, and I think from a commercial standpoint, that balancing game is where we spend a lot of our time trying to optimize for lowering false positive rates while at the same time finding more bugs and also scaling up to large programs. These are conflicting factors.
Okay, excellent. So You just mentioned as a commercial company, you obviously have commercial clients, but my understanding is you have a program called Coverity Scan that also provides a service to the open source community. Could you tell us a little bit about that?
Absolutely. One of the things we found is that a lot of commercial software is not really fully commercial software. They use a lot of open source. Some statistics show that even very large commercial projects might contain 60 to 80% or more of open source software inside of them if you look at this pure line of code count. So what we did was we developed a scanning project for open source projects. It was originally started with the Department of Homeland Security, but ultimately we decided to fund it ourselves. And what it does is it allows open source projects to submit their code to us on a regular basis, get the analysis results in the cloud, and fix them for free. So it's great marketing for us, but it's also, I think, a good service for the open source community. They fixed tens of thousands of defects. Some quick statistics on Scan. We just crossed 500 million lines of code in Scan that's being analyzed on a weekly basis, and over 2,500 projects across many different languages, C, C++, and Java right now. So it's a very successful project, and if you have some open source code that you want scanned for free, you can certainly submit it to scan.coverity.com and try it out.
Okay, fantastic. Let's see. I'm wondering whether you mentioned a moment ago doing your analysis on C and C++ and Java. Is it the case that static analysis is more difficult on some of those languages as compared to other ones?
C and C++ are generally very difficult languages to analyze, right? Because they don't have memory safety, but also they're good languages to analyze because they don't have memory safety. I mean, from our perspective, the worse the language, in a sense, the more ways that you can, shoot yourself in the foot, the better for us, in that we can find more defects for you. And so, hard is good in that sense. It's also just difficult to parse languages like C and C++. Java's got it's just a lot less diversity when it comes to the compilers and the kind of different language variants there are. But then there's all these dynamic languages, right? Think JavaScript or Python and Ruby. These have different challenges for static analysis, and I think there are static analyzers out there that do analyze these programs in these languages, but they are generally more shallow in nature because it's hard to really get the same level of data that you do from a static language in these dynamic languages just purely from static analysis. So it can be difficult. I think it's still a research area for us. I mean, we're definitely exploring that, and I think for the academic community as well, it's still very much a research topic.
Do you are you suggesting then that you have plans, or you would hope to at some time in the future analyze things like Python or JavaScript, other pretty popular languages, but ones that don't fit into this sort of statically typed, traditional compiled language sort of framework?
I wouldn't claim that we have plans, but I wouldn't close that off either. I have to be a little careful when talking about the future, but I would say that we're certainly open to looking at all kinds of software in all languages ultimately. But I'm not claiming anything today.
Okay, fair enough. So you briefly mentioned a little while ago dynamic analysis as compared to static analysis, and you discussed a little bit of some of the trade-offs. Do you support dynamic analysis in your Code Advisor tool? And if so, what sorts of things do you use it for as opposed to static analysis?
Yeah, there are some uses of dynamic analysis within our static analysis product, and we use it primarily to vet certain things that are hard to determine purely statically. So, for example, inside programs there might be validation routines that check that something is a valid credit card number, or that it's a valid escaping routine for cross-site scripting in certain contexts. These kinds of routines you can analyze statically, but we found that a relatively simple dynamic approach, testing approach, can be very effective at determining if these are, for example, proper escaping routines. And so they don't produce a sound answer, but almost always they are very, very correct, because it's very unlikely that we'll miss something if we're fairly exhaustive. So that's how we use dynamic analysis. So there's certain core problems that are easier for dynamic than static.
It sounds like these two things are complementary. That is, I could imagine you could use your static tainting analysis to find out, well, is a sanitizer routine, is an escaping routine actually being used on all program paths, and then separately using the dynamic analysis to determine, well, is this actually a good escaping routine now that we know that it's being called?
Precisely, precisely, and that's generally, at a high level of abstraction, that's what we're trying to do, is essentially leverage the strengths of both to augment the analysis and make it smarter.
Do you, I know that in the area of data race detection, trying to find bugs in concurrent programs, there seems to be more emphasis these days anyway on using dynamic analysis to find those sorts of bugs, because it's very hard to consider all of the different thread interleavings at compile time. Is that something that that you guys do as well, or is that maybe something that you might do in the future or leave to
Right, so we do have analyzers that detect concurrency bugs. So things like race conditions, deadlocks, and so forth. It's an area that is difficult, I would say, but we do have detectors that do a pretty good job at finding a certain class of these kinds of errors. In general, it's one of those areas where static analysis can provide some coverage if you write your application code in a certain manner. So for example, if you have fairly consistent use of locks in your application, there are many kinds of defects that we can detect for you. But if you have fancier concurrency mechanisms, you have lock-free data structures, and you have to be very careful how you use them, and like things like this, it can be more difficult for static analysis to just understand all those nuances in your application. So while we generally cover concurrency in the broad strokes, it depends on how you use concurrency and what you mean by it in a specific application.
It sounds like it comes back to this point that static analysis has to look at fairly limited properties, and in the case that you can express the property in a simple way, like this lock is always held when this variable is always accessed, then that's something static analysis can hunt around for. But when the property is a little bit more subtle, it's harder to get static analysis to manage all of those different trade-offs of scalability and so on.
I would say I wouldn't claim that it's necessarily not possible or that it's hard. It's just from a commercial standpoint, there are fewer and fewer people doing that kind of advanced work, and they generally have smaller and smaller pieces of code, right, in which to look at with those complex kinds of usages. And so as a result, from a commercial standpoint, it might not be worth it to kind of delve too deep into corner cases, essentially, right? The majority of the code that uses concurrency, for example, in Java, is using fairly straightforward synchronization primitives that are built into the language, and those we can handle just fine. So I think it's more of a trade-off in terms of what's worth investing in from a commercial standpoint. But yeah, I mean, there are algorithms that can deal with complex data structures and concurrency primitives that have been explored in research. And if there's enough demand and someday some concurrency primitive becomes really popular, it's something we would certainly consider.
Okay. So you just mentioned that commercial viability was one factor in determining whether you design an analysis or not for your product.
Right.
Could you say a little bit more about maybe other factors that go into deciding? How do you decide when to do something as a static analysis to extend your product to look for some problem?
Yeah. One of the factors is the criticality of the defects, right? So recently we had Heartbleed, right, which is a pretty severe security vulnerability, and we quickly determined that there was some way that we can detect this defect, and so we augmented our analysis to do that. And so there are cases like that, and there's other cases where we try to develop things that our customers have asked for, right? So we listen to our customers, they give us feedback about whatever kind of defect that they are interested in finding. They give us some examples, and we examine that, and we build prototype checkers. And if those checkers can be developed in a way that don't have excessive false positives and still detect the errors that they're interested in, then we consider shipping them, right, over time. But there's certainly cases where people have sent us examples of defects which we give up on, right? And they're just either not detectable easily with static analysis, or we don't have the time to get to them, or the false positive rate might be too high, right? In the latter case, we also do things like have optional flags that essentially allow only certain customers to turn those on because they really want it. But if you did it with everybody's code, you'd end up with a lot of false positives. And so there's that option as well.
Are you able to trial run your detectors on your existing customers' code? In other words, let's say that customer A requests a particular feature, and you want to decide, okay, is it going to work with the false positives and so on? I imagine you can certainly use the scan project to help you out with that. You have all this open source code to help you determine false alarms. Are you also able to ask your other customers to trial run these ideas and see how well they pan out?
Right. So we have a couple mechanisms for that. One is we can help the specific customers that ask for it to try out a beta version of the analysis. Another thing that we do is we run a lot of trials. Right. So these are cases where we go out to not customers yet, prospects, I would say, and we give them a chance to run our analysis and see the results. And sometimes, as part of trials, the sales engineer that we have that helps with the trial will kind of let them know if they're interested in a particular kind of defect that we know we have prototype for. We might turn it on and give them an opportunity to see what the results might look like, right? If they actually use that. So that does happen as well, and it gets us some feedback about things that would be hard to gather otherwise, as you might imagine, since these code bases are mostly proprietary.
Yeah, I was thinking that I believe it's the case that I'm forgetting the name of the company. They have the business model where you send them the code and they run the analysis on it and send you back a report.
Right. Veracode is what.
Veracode, yes, that's it. So they would have the benefit of they have access to all of this code, whereas I suppose if you send your product to your customer, you give them the option of whether they send data back to you or not.
Right. So so one of the differences between Veracode and us is that they analyze binaries, right? And so as a result, they don't actually need the source code, or at least not the full source code of the application, whereas we're analyzing the source code. So it's the one difference, and the net effect of that is that we send our product to the customer, and they run it on premise typically.
So Coverity was founded, wow, I mean, I was looking on your webpage, 2003. It's been,
That's right.
It's been a while, right? Sorry, 2002?
It's been, yeah, I guess 12 years, 11, 12 years now, yes.
Yeah, wow, so time flies.
Yeah.
I just remember you being a trailblazer at the time, and that static analysis companies existed, but it seemed like the market sort of came of age when you guys hit the scene. I wonder if you could reflect back on all that's changed from the time that you started until today, and what were the problems in the past? Which of those problems have been solved from, say, a practical point of view, and what problems do you see in the future for this industry?
Right. Wow, in 2003, the world was a very different place. I think static analysis was not really much of a commercial market at all. There were a handful of products. If you look at C, C++, there was product like Lint, and there's a few others on the marketplace, but the aggregate size of the market was very, very small. I'd say commercially, at least, there were very few people working on static analysis as a product, right? Since then, Coverity grew to about 300 people as of 2014. We were just acquired by Synopsys this year, so it's kind of not exactly the end, right? Because it will continue under the Synopsys rubric, but it's certainly been a long journey, and I think the market has matured a huge amount, right? I think back in 2003, static analysis was considered kind of, wasn't really commonly used, I would say, at least not in practice in large development organizations. And today, I would say if you're doing C, C++ development, it's not, absolutely required, right? But it's getting close to that point where, it's kind of scary to not do static analysis if you're developing a million lines of code application or up, certainly. I think that's a huge change from where we started, and it's a good one. I think it means that the software engineering practice is gradually maturing and new tools are being integrated in. The other thing is security has just grown in terms of importance so much. I think in the past when we started, it was all about quality, right? It's about finding crashes and things that could cause your customers to come back and scream at you. But now security is such a high-profile problem and something that's first and foremost in developers' minds, or at least within organizations. Like maybe not individual developers, but in terms of the organizations they work for, they care a lot about this problem, and that's really changed the focus of what kind of static analysis is being worked on in a lot of companies, including ours.
Do you? We spoke a little bit before about the core technology, like, say, the tainting analysis.
Yeah.
Did you find that when the security became more of a focus and maybe Coverity started working more on security. Did you have to develop new core analyses, or did you find that many of the analyses you'd already developed could be retooled to work for security?
It was a combination. There were certainly algorithms that worked fine for security checks, and there were other ones where we had to invent entirely new engines. So that tainting engine I was talking about was something we added specifically for security. And that was something we had in some form in the past. We got much more serious about it when we realized that security issues really required you to have a good tainting analysis. And I think that it's among many problems that we had to tackle when we changed gears like that. Another is reporting, for example, the kind of reports that security organizations care about and what's reported on them is very different than what a quality-oriented kind of report might look like.
So I guess this question, there are two questions that are two sides of the same coin. So one is, what challenges do you see for the industry going ahead? And on the flip side of that, what are some barriers to the practical adoption of static analysis today, as far as at least companies believe?
Yeah. In terms of looking ahead, I think there's lots of room for expanding the use of static analysis. You mentioned languages before. I think that's a huge one, right, in terms of getting more access to static analysis across these new dynamic languages where they don't even have the basic typo analysis in many cases, right, that we take for granted in static languages. But I think that if you look at the industry as a whole, what's keeping static analysis from being used more, right, and being more common practice? I think part of the answer is that it's just a change in culture and mentality. It's very difficult for people who aren't used to dealing with this new source of defects, right, to deal with that, right? Suddenly they turn this analysis engine on and they're faced with a few thousand bugs, and they don't know what to do with that. They already have too many bugs in their database and they can't fix them all anyway, so why add a few thousand more? But the thing about static analysis bugs is that they're pinpointed in the code, right? There's an actionable there's no need to kind of reverse engineer how the bug occurs. It's kind of a root cause. And so, changing the mentality about how you can efficiently address these defects earlier in the cycle, and getting people to realize that if they're proactive about fixing those, they might have fewer of those hard to understand defects in the field in the future. It's difficult. It's kind of like getting people to exercise or have a good diet. Before you have a problem, it might seem like, oh, that's other people's problem, not mine. But until it's your problem, right? And then you take it seriously. So I think that gradually organizations are realizing they do need to be more proactive about ensuring security and quality in their applications, and that's where we can help.
So this has been great. It's been really interesting to hear about, especially the commercial perspective on static analysis. I wonder if you, in your experience in working with companies and thinking about how static analysis fits in the overall process of making programs more secure, are there other tools or techniques that companies talk about that you have to think about when you write your tools so that you fit within the overall ecosystem? Things we mentioned already, maybe testing, penetration testing perhaps, or manual code review. Are there other things that you hear about? Maybe the use of certain operating systems or deployment environments, things like that static analysis has to think about?
Yeah, I mean, I think the most sort of direct touch points for static analysis include build systems, right? So build systems are complicated, and integrating with them so that you can actually see all the code is non-trivial usually. Another example is the use of bug tracking systems. If you want to get your bugs fixed, often you got to push them into a system that people are already using for assigning work to each other, right? A third is source control systems, right? These are systems that keep track of who wrote what code, and without that information, it's hard to assign these defects that pop out of static analysis to a person, right? And if they're just sitting there in the ether, nobody works on them. So these are the common integration points that we have. But the big picture is that you need to really integrate with the flow that developers use in each company, and each company has its own unique, often homegrown kind of methodology for how they do development, at least in the details, right? And integrating with all of those details is often a challenge, and is part of the reason why professional services or just somewhat champion inside the company that understands how to put this new thing, this foreign thing, into the organization is often required to get static analysis to be effective.
Okay, great. I wonder if there's anything we haven't talked about that you think is important that people ought to know about static analysis or about Coverity. Just any parting thoughts?
One thing that we just launched recently is a new version. It's not Coverity Scan, but it's called Code Spotter, right? And it's essentially a free service for not just open source projects, but kind of homegrown projects as well. So if you have some code on GitHub that's written in Java today, then you can use Code Spotter on it and get analysis results. And so that's an interesting new dynamic, I would say, is this idea of putting code in the cloud and development in the cloud, and it's a trend that I think actually does benefit static analysis technologies, and that is emerging. We'd like to kind of ride that trend as well, and help developers that want to do that kind of development move more of their flow into the cloud, and static analysis should be a part of that. So we're excited to see that. I think kind of the big picture is that if you care about security, if you care about quality, there's, like I said, many different things you can do, and I think static analysis is one of those things, and it's one of the things that works, kind of while you code, in a sense, right? Like while you're first putting out that code, you can actually get feedback really early in the process. And unlike techniques that wait until, let's say, an expert comes in a few months later or years later to look at your code, you can find it now. And I think that's something I hope developers can keep in mind, that security is part of their jobs, as well as quality, and you can't just rely on outside expert to just do it for you. It really requires developers to get proactively involved, and to the extent that we can help that, we're happy. But I'm also happy if developers are just more aware of the problem and just can learn more about it and be more proactive about fixing bugs earlier.
Fantastic. That's I have to say that's part of my goal in this class, is that too often people think of security as something you can solve by putting a box on the edge of your network, and really that's not going to scale. The way you're going to solve your security problems is to build that network better in the first place.
Exactly.
So one maybe fun question is, have you used Coverity Code Advisor on itself, right? It's a program and you can run it and evaluate itself. How does it do if you do?
Yes, we do analyze our own products, and we do have a dashboard that's sitting in our kitchen that everyone can see at lunchtime, and so we keep a close eye on our analysis results. And we found bugs in our own product before, thankfully before shipping for the most part. And we track every release. We say no new defects, and we whittle down the legacy defects if there are any. Many products are at zero findings at this point. So we definitely believe in it. I mean, we're believers in what we build, and we use it for sure.
Okay, well, fantastic. So I want to thank you. This has been Andy Chou, who is the co-founder and chief technology officer of Coverity, which is a leading provider of software quality and security testing solutions. So, Andy, thanks so much for taking the time.
Thanks, Michael.
All right.